This is question 16.8, number 2. It's the first of the Stokes theorem questions. And again, Stokes theorem allows us to take a surface integral, the same thing we've been working on. It's basically a flux, except now it involves calculating the curl first. So it's the curl of a vector function, and then we're sort of measuring the divergence of that curl. And it turns out through Green's theorem that we can evaluate this instead just around the boundary, the closed loop integral of f dot dr. So that means a single parameter around basically the edge of this particular surface. So we could go ahead and try and take the curl of this and form a new vector from it, and then we could parameterize this and then dot that parameterized cross product with the curl of this vector, and then do a 2D integral. And we could perform that for this one. This one's not such a bad candidate, but because this is fundamentally a circle in the xy plane, that just really lends itself really well to this. So I'm going to single parameter this guy and go ahead and solve this side instead. So the parametric we want to use is r of t. We can get away with one parameter, and all I want to do is parameterize this guy in the xy plane. So when z is equal to 0, this is a circle. So to make a circle of radius 1, I just need cosine of t, sine of t, and then 0. Again, since I'm doing it as a curve in the xy plane, I don't really have to care about this guy having a surface on it. If I wanted to do the surface integral, of course, I would need to take that into account, but I don't in a single parameter, so that's why I use t. And then, of course, to find dr, I need r prime, and r prime is going to be negative sine t, cosine t, and still 0, and that's dr. Or excuse me, dt. So now I just need to parameterize this guy so that I can see what it makes in terms of its new function. So f is going to be equal to, and again I'm going to replace all the x's with cosine t and all the y's with sine t and all the z's with 0. So it's good that the z component goes away. So the x component is going to be cosine t sine squared t. The y component is going to be negative cosine squared t sine t. And the z component is going to be 0. So there it is. And now all I need to do is dot it because we're doing this around the full circle in the xy plane. T goes from 0 to 2 pi. And again, that's just because of the parameter I picked. So we're ready to go. Let's dot these. So it's going to be negative cosine t sine cubed the y component's going to be negative cosine cubed sine t plus 0, and I'll integrate this from 0 to 2 pi dt. So there it is. We're actually evaluating this integral by simply parameterizing the surface in the xy plane and then going around it in the counterclockwise direction. Integrating this, it turns out to be 0. So had we done all the work for this, it would have turned out to be 0 anyway. And as a matter of fact, it actually turns out to be 0 as soon as you write the parametric for this and then find its cross product. You'll see that that guy dotted with this, there's zeros in components where things match up, which is why it turns out to be 0. Nonetheless, I don't think that's an easier way to go. It would have still involved doing the curl for this, and then parameterizing, and then you'd have had to substitute into the equation with the parametrics in u and v. I still think this was the easier way to go.